This video is for number 64 of section 8.6. A 0.005 kilogram bullet traveling horizontally with a speed of 1 times 10 to the third meters per second enters an 18 kilogram door, embedding itself 10 centimeters from the opposite side of the hinges as in the figure below. The 1 meter wide door is free to swing on its hinges. Okay. So the bullet is traveling horizontally with an initial velocity. Initial velocity of the bullet, v sub bi, is equal to one times 10 to the third meters per second. This bullet has a mass equal to 0.005 kilograms, and it enters an 18 kilogram door, which will be m sub d is equal to 18 kilograms. It hits the door 10 centimeters, 0.1 meter away from the end of the door opposite to the hinge. So that means the radius of the bullet, once the door begins to rotate, is 1 meter of the door minus 0.1 meters. So this distance is 0.9 meters. So we'll call that the radius of the bullet. And we also know that the length of the door is equal to 1 meter. Part A asks, before it hits the door, does the bullet have angular momentum relative to the door's axis of rotation? And the answer to part A is yes, and we can show this through an equation. So initial momentum is equal to the initial moment of inertia times the initial angular velocity. The moment of inertia for the bullet entering once it swings in the door is the mass of the bullet times the bullet's radius squared. And for the initial angular velocity, we can recall that linear velocity is equal to the radius times the angular velocity. So we can put the initial velocity of the bullet over the bullet's radius in for the initial angular velocity of the bullet. And we can cross out one of these, radius, and the initial angular momentum is equal to the mass of the bullet times the radius of the bullet times the initial linear velocity of the bullet squared. And we know that going into the door, the bullet does have all of those quantities, so that can prove to us that it has angular momentum. Part B asks, is mechanical energy conserved in this collision? Answer without doing a calculation. When the bullet hits the door, and then the door and the bullet travel together. This is an example of a perfectly inelastic collision because the objects stick together, and mechanical energy is not conserved in perfectly inelastic collisions. Part C asks, at what angular speed does the door swing open immediately after the collision? The door has the same moment of inertia as a rod with an axis at one end. So that part in parentheses is just telling us what equation we'll need to use for the moment of inertia of the door, which will be 1/3 times the mass of the door times the length of the door squared. So in order to find the final angular velocity of the door and the bullet, because they stick together, we can use the conservation of angular momentum. So the initial moment of inertia times the initial angular velocity is equal to the final moment of inertia times the final angular velocity, which is, in fact, what we're looking for. So we already know that the initial moment of inertia from part A is equal to mass of the bullet times the radius of the bullet times the initial velocity of the bullet. And then we need to look at the final moment of inertia. So that would include the moment of inertia of the door plus the moment of inertia of the bullet, and this will be multiplied by that final angular velocity that we're looking for. The moment of inertia of the door, as the hint gave, is 1/3 times the mass of the door times the length of the door squared. And the moment of inertia of the bullet is the mass of the bullet times the radius of the bullet squared multiplied by the final angular velocity. So we divide each side by this term to solve for the final angular velocity. And now we can put in the numbers that we know. So we know the mass of the bullet is equal to 0.005 kilograms. The radius of the bullet is 0.9 meters. Times the initial velocity of the bullet, 1 times 10 to the third. Meters per second, divided by 1/3 times the mass of the door, 18 kilograms, times the length of the door squared, 1 meter squared, plus the mass of the bullet, 0.05 kilograms, times the radius of the bullet squared, and this gives a final angular velocity of 0.749 radians per second. So let's go back up. Part D asks, calculate the energy of the door bullet system. Enter the kinetic energy of the door bullet system just after the collision. So this is asking, we can say for the final kinetic energy, and this will be a rotational kinetic energy. So we can say K sub RF is equal to the final moment of inertia, or 1/2 the final moment of inertia, times the final angular velocity squared. 1/2, so remember we need to include the moment of inertia of the door and the bullet, the mass of the door times the length of the door squared, plus the mass of the bullet times the radius of the bullet squared, times that final angular velocity we just solved for. Let's put in the numbers that we know. 1/3 times 18 kilograms times 1 meter squared plus 0.005 kilograms times 0.9 meters squared, all times 0.749 radians per second. And in your calculator, this will give you a final rotational kinetic energy equal to 2.25 joules. Part E, let's read again. Determine whether the energy of the door bullet system is less than or equal to the kinetic energy of the bullet before the collision. So we can find the kinetic energy of the bullet before the collision using K sub L. This will be a linear kinetic energy. Initial is equal to 1/2 the mass of the bullet times the initial velocity of the bullet squared, 1/2 0.005 kilograms times 1 times 10 to the third meters per second squared. And this gives an initial kinetic energy of 2,500 joules. So the answer to part E is the door bullet system has less kinetic energy than the initial